Question number 1 says, deduce the formula of the conjugate acid of the following. So if it's becoming an acid, it was a base, and bases accept an H plus ion. So that means SO3 would accept an H ion, and I'd write it at the beginning because H2SO3 is a common acid. The polyatomic ion goes at the end when there is one. But now this has a -1 charge because it picked up an H plus. With B, this is an organic or weak acid, CH3NH2. The CH3 is, the carbon's already full. It's got 3 hydrogen and it's bonded to the nitrogen. The nitrogen is the one with room to pick up an H plus because it's got a lone pair there. So it's going to be CH3NH3. And I don't know how you remember, and it's going to have a plus with it. I don't know how you remember if the H should go at the beginning or the end. I'm not sure if IB will deduct points as long as you know it gains the hydrogen and as long as you get the charge correct. Gaining an H plus ion, you have to account for that charge. So with C, I've got C2, H5, COO, and I pick up an H plus, so the H plus and the minus cancel out. D, I have NO3, so this will become HNO3 with no charge. E, I would become HF with no charge. And F, HSO4 is going to become H2SO4 with no charge. So those would be the conjugate acids for question number 1. And I'm going to pause here and erase these, so go ahead and pause yourself if you need some time with this. Question number 2 then is somewhat similar. It says deduce the formula of the conjugate base. So bases now have lost, it was an acid, it's becoming a base, so that means it's lost in hydrogen, and I'm going to lose a positive charge with it. So H3PO4 for A is going to become H2PO4 with a -1 charge. B is going to become CH3COO, and that last H is going to be lost, so it's going to have a minus charge. C is going to become HSO3 with a minus charge. D is going to become SO4 with a 2 minus charge. E is going to become just O2 minus. And F is going to become Br minus. So those are my conjugate bases. Again, I'm going to pause and erase these before I move on to number 3. For number 3, it says, identify the Bronsted-Lowry acids and bases and the conjugate acid-base pairs. So if I look at A, CH3COOH, on the other side, it's given up a hydrogen, so this is my acid, and NH3 is gaining that, so that's my base. That makes NH4 my conjugate acid, and CH3COO minus my conjugate base. With CO3 2 minus, it gains the hydrogen, so this was the base on this side. The H3O gives it up, so it's the acid. And on the other side, H2O is my conjugate base, and HCO3 is my conjugate acid. And for C, NH4 plus is going to lose a hydrogen, so this is my acid. NO2 gains it, so that's my base, making this my conjugate acid and my conjugate base. And then going on to number 4, it says, show by means of equations how the anion in K2HPO4 is amphiprotic. So they're only talking about, for number 4, they want to know why HPO4 minus is amphiprotic. Well, I could add H2O to it, and that H2O could take the other hydrogen and become H3OP, H3O plus, and leave behind the PO4. This should actually be, this should actually be a -2 here because you took a K2 off. So this is going to become PO4 minus 3, or the HPO4 2 minus could be added to the H2O, and it could take the hydrogen and become H2PO4 minus and leave behind the OH minus. So it can both gain and lose the hydrogen, which is what we mean by amphiprotic. Question number 3 wants to know, what is the conjugate base of HSO3? So if it's becoming a base, it was an acid, meaning it's going to donate the hydrogen. So that's going to leave SO3, but instead of just a -1, it's going to be SO3 with a -2 charge. So B would be my correct answer. On number 4, which of the following can be described as amphiprotic? OH minus could gain a hydrogen and become H2O, or it can lose a hydrogen and become just oxygen with a -2 charge. So that's amphiprotic. B, NH4 can lose a hydrogen, but it cannot gain a hydrogen and become NH5. Nitrogen can't expand its octet. BeCl2 also cannot have an expanded octet. It can only bond 2 single bonds, so that's full. And SO4 has no hydrogen to lose. So C and D are kind of ridiculous because there's no hydrogen to give up, so we know they can't be acids. And NH4 has hydrogen to give up, but no more room to gain hydrogen. So only A could be described as amphiprotic. 7, in the reaction, and I'll let you read that, the 2 Bronsted-Lowry acids are, so if I look at the left side, the CH3OH gives up a hydrogen, and in the reverse, it's the NH3 giving up the hydrogen. So that would make D my correct choice. CH3OH and NH3 are the acids. One's considered a conjugate acid, but still an acid. And then moving on, number 10 says, which of the following are conjugate acid-base pairs? So it says HNO3, NO3 minus. That seems like it's a conjugate acid-base pair. 2 says H2O and OH minus. That also is a conjugate acid-base pair. And then H2 and H plus, that is not a conjugate acid-base pair. And it's a little bit tricky because it appears like it could function as an acid-base pair, but the reality is H2 doesn't readily dissolve in water and donate a hydrogen. So even though it looks like on paper like it would be possible, it doesn't occur. So B is the only choice there, or is the correct choice, I should say. And 12, which of the following statements is the defining property of a Bronsted-Lowry base? Bases are proton acceptors. So donates protons? No, not true. Produces OH ions? Sometimes, but not always. That's only according to the Arrhenius definition. Conducts electricity? That's true, but so do acids, so it's not the defining property. Accepts H plus ions, that's the defining property of a Bronsted-Lowry. So even though B and C are true, they're not the defining property and what sets it apart from other definitions like the Lewis model or the Arrhenius model.